All right, so in 3.3, we're going to continue looking at reducing matrices. All right, and we have taken a matrix. Here's an example of one. We've taken a matrix and put it in row echelon form, forming the little staircase with the leading terms. And each leading term had zeros below it. So just to review, let's real quickly, I'm going to real quickly pause this and work through the process of putting this particular matrix in row echelon form. We'll just work through it together here. All right, so the first thing we're going to do is we just quickly look, and I always like to have this upper left entry to be 1. That's the ideal. All right, so it's all good to go. So what I'm going to do is I'm going to take -3 times row 1, add that to row 2, and replace row 2. So -3, -6, -3, -12. And then row 2 is a 3, 8, 7, 20. So the replacement will be 0, 2, 4, and 8. Okay, now I'm just going to highlight this. I'm going to keep track of that. That's going to be my new row 2. Okay, but I know that I also need to get rid of this term. So I'm going to kind of double down here, and I'm going to do 2 eliminations at once. So I'm going to go -2 times row 1, add to row 3, and that will replace row 3, just to save a little time. So -2, -4, -2, -8. Row 3, 2, 7, 9, 23. And so when we add those, we get this right here as our new row 3. Okay, so now we do need to write down our matrix. So we've got our leading term right there. And then new row 2, so we've created a 0 below that leading term, and new row 3. Okay, so what's left is to create a 0 right there, right? We're looking for this little triangle of zeros as kind of our goal, if we can get it. So to do that, we're going to go, let's go 3 times row 2 plus a -2 times row 3, and we'll replace row 3. So 3 times row 2 looks like this, 0, 6, 12, and 24. -2 times row 3 is 0, -6, -14, and -30. When we add those up, 0, 0, that's what we want, -2, and a -6. And I see right here, I could have done this with my row 2, but I see right here that I'm going to add one more row operation here. I'm going to take that new row 3 that I just created, multiply it by -1/2, and replace row 3. Right, so that new row, there's my row. I'm just multiplying by -1/2 because that will give me a 1 in that as the leading term. So here is the matrix. Let's do this. Try this a little bit. Here is our matrix. 1, 2, 1, 4, 0, 2, 4, 8, 0, 3, 7, 5. No, we got a new row 3. Let's use it. 0, 0, 1, 3. Okay, now it's important to remember that each of these matrices that we created here was the original. These two are equivalent matrices, which means they have the same solutions as the original because we obtained them by using elementary row operations. Okay, so at this point we could solve this system. Okay, we're going to go a little further. Let me also mention this. This matrix, which is in echelon form, right? That's in echelon form. We've got that little stair step of going on there of leading terms with all the zeros zeroed out. That is not unique. So what that means is if I happen to use a different sequencing or different elementary row operations altogether, I will get a different row or echelon matrix. All right, it'll have the same solutions, it's still equivalent, but it will look different. Okay, so just remember, just understand that. And that process is Gaussian elimination. That's what we used here. All right, so what we're going to do now is we're going to use a process called Gauss-Jordan elimination. So it starts with the Gaussian elimination to get echelon form. And what it's going to do is it's going to put our matrix in what's called row reduced echelon form. And what that means is this. In echelon form, we have our leading terms that are stair-stepping, right? But we also have the fact that there are zeros, only zeros below any leading term. In row reduced echelon form, we're going to also get zeros above the leading terms. So I need to create zeros in those three positions. And that process is using Gauss-Jordan elimination. It's the same thing, really. We're still using elementary row operations, but we create zeros above our leading terms. Now we always do it in this order, right? In fact, you'll always kind of go counterclockwise. 1, 2, 3, and then you'll move over here 1, 2, 3. Or another way of saying it is you'll get your leading term and then zero everything out. Get your leading term, zero everything out below it, right? And then once you've zeroed everything below, here's a leading term, but it doesn't have anything below it, right? Once you've zeroed everything out below, then you start zeroing everything out above your leading term. So you'll go after the 4 and the 1, and then you'll go after the 2. All right, so that's where we're at. And that's what we want to do. We want to get zeros here and here using Gauss-Jordan elimination, thus giving us a matrix in row reduced echelon form. So the process is pretty much the same. We're going to go after the 4 first of all. So we're going to go -4 times row 3 plus row 2 replace row 2. Okay, so -4 times row 3 looks like this, -4, -12. Row 2 is a 0, 2, 4, 8. And so when we add those, we get a 0, 2. Now, the 2 doesn't bother us. We need the 0 there, and we need -4 there. Now, that's going to be our new row 2 here in a second. But we might as well go ahead and eliminate the 1 there as well. So that's easy. That's just going to be -1 times row 3. Add that to row 1, okay, and replace row 1. So -1 times row 3, 0, 0, -1, -3. Row 1 is 1, 2, 1, 4. So when we add those, we still have the 1, still have the 2. We were after the 0, and there we go. That's going to become our new row 1. So let's write down our new matrix. We got a new row 1, which is 1, 2, 0, 1. A new row 2, which is 0. Let's try that again. 0, 2, 0, -4, and then the row 3 is set. Okay. And so we're good. We've got our 2 zeros above this leading term. Okay, so what we now need to do is back up. Here's a leading term. Let's get that to be 0. Okay, so we're going to go -1 times row 2, add that to row 1, replace row 1. Okay, and that's going to look like this. -1 times row 2 is 0, -2, 0, 4. Row 1 is 1, 2, 0, 1. And let me just say this, you have to get these 2 zeros first, so you really need to be working in this counterclockwise direction. Okay, so 1, 0, 0, 5. That's our new row 1. Now, probably some of you wanted to do this other thing. We'll talk about this here in a second. Okay. So there we go. We've got our zeros, we've got our leading terms. Okay, leading terms here, here, and here, and then zeros below them, and then zeros above them. Okay, Now the last thing, and you can save this to the last thing to officially get it in row reduced echelon form is you want all your leading terms to be 1. So you can see that we're pretty close. Let's do this, give ourselves just a little room. We're pretty close. We've got 1 there, 0, 0, 5. But our second row doesn't have a leading term of 1, so we know what we'll do. We'll just take 1/2 times row 2 and replace row 2. Okay, and that's what will happen here. So 0, 1, 0, negative 2. In other words, you're dividing everything by 2. 0, 0, 1, 3. And that is the row reduced echelon form. You've got your 1s as your leading terms. Now we call this kind of the main diagonal of the matrix, and then you've got zeros above and below. You got these little triangles of zeros. Okay. Now here's the thing about row reduced echelon form. Okay. Number 1, it does not matter the sequencing that you use for any of your basic row operations, elementary row operations. You will always end up with the same thing. I could do this. I could put this matrix in row reduced echelon form. Somebody else could put it in row reduced echelon form. Somebody else could put it in row reduced echelon form, and we would all end up here. As opposed to, like I said earlier, when we just went into echelon form, everybody's going to end up with something different if they use different elementary row operations. Okay, so in one sense, the thing about the row reduced echelon form is it's the simplest, most reduced equivalent matrix to the original. Okay, I kind of think of it as, when we reduce fractions, we always want to reduce them to their lowest terms. I think of the row reduced echelon form of a matrix as its lowest terms. It's the lowest and most simple equivalent matrix to the original, and it's always the same. Okay, now that's one thing about row reduced echelon form. The other thing about row reduced echelon form is if it's a system that we're talking about, right? If this matrix comes from a system, because it's entirely possible that we just take a matrix that has nothing to do with the system and put it in row reduced echelon form. But if it comes from a system, then I want you to just notice, once it's in row reduced echelon form, once we transform back into a system, look what we've got. Whoops, let's try that again. We've got our solution staring at us right in the face. Those 3 equations, those 3 rows transform into those 3 equations, which are just the solution to the system.